What's up, team and YouTube? Welcome to the auditorium. I'm excited because we're back with some PE practice problems today. And I'm going to be getting into some of my favorite, it's not time yet. It's not time yet. I'm going to be getting back into some of my favorite. I'm going to be using the AISC Steel Manual 15th edition to help us get through this. I know you're doing CBT, but I'm pretty sure they do provide that in a digital form. So get a hold of it and follow along. Big, huge, scary problem, I know. At first glance, you have this huge figure, you got a bunch of variables, you got a bunch of numbers. Pump the brakes, don't panic. This one is actually more simple than it appears. I'm gonna prove it, or I'm gonna get to the solution doing two different methods. You could choose the one you want to use and are more comfortable with. One is faster than the other, I think, but it all depends on how you use it. You have a beam. These beams are spaced at 10 feet on center. So if we look in plan, 10 feet, 10 feet, and this right here is this beam. The total service load reaction in kips at support A is most nearly what? So they want us to know what is that reaction right there. And our assumptions are all loads act simultaneously. So we don't have load combos that we got to worry about, or some happening and trying to figure out worst case scenario. Neglect beam self weight. All right, so they do give us the size of it, but they say don't worry about the self weight, so that'll speed up the process. And then live loads are non-reducible. This is something I don't think you'd run into in the PE exam. It's more an SE question that is like a morning SE type question, is live load and live load reduction. But for the instances here, that just means that you can't alter or reduce your live loads. So that's great. So that means all of the loads given here are just what you're using. Because they also say, you're like, well, why don't we do load combos? Because they say service load reaction. So service load is just unfactored loads. All right. Something I always try to note with the PE exam problems is take a look at what they provide you for answers. If they're super close together, all right, you gotta do the right equation and hit the nail on the head to get the problem right. But if they're spaced far apart, and I would consider these spaced far apart, that means if you were in a crunch and you didn't know how exactly to do the problem, you could use some mental math or some engineering judgment or quick tips and tricks to hopefully get you decently close to the final answer. So don't forget that, and use that kind of little tip when you're taking your exam, is look at the answers provided. Are they super far apart, or are they super close together? Method one, I have my steel manual, and I'm going to be going to table 3-23. So our shear and moment diagrams, all those beauties right there. I'm going to break this up into the different loads and get their contributing force at reaction A. So I'm gonna do chunk 1, we'll call that 1, chunk 2, chunk 3, chunk 4, and chunk 5. All right, chunk 1, let's just get the load. This one's easy because it's just concentric with your reaction A, so there's no distributing part of the force to some other part of your system. It's concentric with A, the force is going straight down into reaction A. And that's just dead load of 320 plus live load of 320. And then it's a 10-foot on-center spacing, which means it has a trib of 10 feet to this beam. So 10 feet, that gets us 6.4 kips. I'm gonna leave the answer in kips because they're looking for a final answer in kips. Always try to help yourself out. And I'm also gonna make that, I'm gonna denote my direction of the force. So downward. Well, chunk 2, I'd flip over to the steel manual, and you will see that on equation 27, so on page 3-217, we have, I'll go green here, we have a beam, propped cantilever type of thing, and we have a bunch of load on the first span, but nothing on the cantilever. So that's good, and then you have, reaction and reaction. And they give you an equation for this reaction. The equation is as follows. All of that gets us 24 kips clean. Well, chunk 3 is really easy. It's just equal to 0 kips. Because for the same explanation that we gave in chunk 1, chunk 3 is concentric with reaction B. So that means all of that load is just going right to reaction B, and it's not getting distributed to any other part of our system. all done with that. Cool. Chunk 4 is, we're gonna go back to our steel manual, and it's actually equation 25 on page 3-216, the page right before, and it gives us the same propped cantilever, but now it just gives us a distributed load on the actual cantilever itself. And again, it gives you, R2, R1, and it gives you the equation to solve for R1. And that spits out 2.07 kips, and that reaction is going upward. Because if you think about this logically, if you put a bunch of load, that's going to load up positively R2, if I can draw that without a squiggle, and that's going to try and actually lift. If this wasn't attached, if this was just resting, well, not on a roller, but if it was just resting on a beam and it wasn't positively connected, you push a bunch down here, that's going to lift that back of the board. But simplistically, that just means you have an upward reaction, because this whole thing is trying to tip over. And lastly, we have chunk 5, which is the railing, and it's just a line load at the very end of our cantilever. And this one, we're gonna go back to our steel manual, and oh my good golly gosh, look at that, equation 26. So the same page, one page further, 3-217, go figure, they're all chunked together. It's like this problem was designed to, once you found that spot in the steel manual, you could move through it quickly. Well, I drew it above there, but it gives a setting here of our propped cantilever, only there is a concentrated load at the very end of the cantilever. So same thing, that's gonna give you an upward reaction, R1 something. All that dumps out 0.33 kips and an upward reaction. And now you're just gonna sum all those reactions that you got for 1, 2, 3, 4, and 5, to get your final reaction at A. I forgot to mention, there is this moment right here. Why didn't I include that moment when I did these forces? I never included it because it doesn't contribute to force A. And it doesn't contribute to force A because that moment is concentric at point B. If it was hanging out over here, now you would have a moment and it would be resolved with a force couple between the reactions, and there would be some amount of uplift force and some amount of downward force that resolved that moment in the beam bending. But it was concentric with B, so it doesn't contribute at all to reaction A. Summation of force at A, that's how I draw it at least, comes out to 28 kips going downward. Just a quick note, I didn't write it out, but the upward force is negative, upward force is negative, downward force is positive, downward force is positive. Oh, look at that, absolutely smushing. C, 28. Number 2, I'm just gonna keep this rolling. I'm not even gonna stop recording. We're just gonna rock and roll here. Method number 2, that I would argue is maybe more quick, but I didn't do this the first time. I did it how I just showed you right here. That's intuitively how I would do it. I use the steel manual frame, the shear, the moment, deflection equations, like all the time. I just enjoy them a lot. I'm just gonna say option 2. And this is just equilibrium equations. So summation of moment at point B, 0 equals, we're gonna scroll back up. We're gonna take actually our reactions that we already found here, but you would have to resolve them. So 6.4 kips is chunk A, and then it's moment arm, force times perpendicular distance to the point that you're applying it, 24 feet, and that's going counterclockwise is positive and clockwise is negative. 6.4 kips times 24 feet. The next chunk is this, so it's not this number anymore, because this was the portion of this full highlighted distributed load that was contributing to force A. But now we need to take that full force. So that full force is 75 plus 125, gets you 200 PSF with a 10-foot trib. That gets you 2 KLF, so 2 kips per lineal foot distributed along this. Multiply it by the full length of the distributed load, 24 feet, to get you your concentrated load. And since it's what what the hell? Blanking out. What do you call this? A uniformly distributed load. Sorry, I'm tripping right now. It's all summed at the center line of the load. So that moment arm is now just 12 feet. And that's acting counterclockwise. So plus 48 kips times 12 feet. Our moment, that just equals 10 kip feet, and then another 10 kip feet. So 20 kip feet at B, and that's going clockwise, so that's negative. So now we're gonna do minus 20 kip feet. And now we have all of our forces to the left of B, which means that they're going to be, most likely means they're going to be clockwise forces, so they'll be negative. Same thing here. So chunk B is concentric with point B, so its moment arm is equal to 0, so we don't have to calculate its force or anything, it's just 0. And then the cantilevered span, chunk 4, is 75 plus 80 times 10 feet of trib times 8 feet gets you your concentrated load at midspan of the cantilever, which is 12.4 kips. I know you can't really read that, with a moment arm 4 feet. Minus 12.4 kips times 4 feet. You'll have your final chunk, which is the point load at the end. So 100 times 10 feet of trib is 1,000. So that's 1,000 kips. So that's just 1 kip. Or sorry, 1,000 kips. That's just 1 kip, 1,000 pounds, with a moment arm of the full 8 feet. 1 kip times 8 feet. And now RA and RB. Well, RB is also concentric with point B, so that has a moment arm of 0, so that goes away, which leaves you with just RA. RA is acting upward. It's an equal and opposite force. It's your reaction, or it's your boundary condition. So RA, and it has a moment arm of 24 feet, and that's acting clockwise, so that's negative. So that's minus RA times 24 feet. Plug all of that in, you get RA equal to 27.2 kips going up, which that to me rounds up to 28 kips, and you're good to go. I'm glad to be back doing some PE problems for all of you. I know that they're not computer-based, testing styles yet. Hopefully I'll get my hands on a few of those. When I do, you're gonna see them. Thanks for watching, thanks for subscribing, and I'll catch you in the next one. Peace.